Let's say you invented a new material. Maybe imagine yourself as a startup company that recently developed a new type of 3D printing filament. How would you test it? To characterize novel, untested materials, you would usually want to know how strong the material is in resisting breakage and how strong the material is in resisting deformation. In other words, we want to measure three quantities: the Young's modulus, the tensile yield strength, and the ultimate tensile strength. To accurately measure these quantities, you previously only have one option: buy a professional tensile tester that costs at least $13,000. This solution is extremely expensive for low-budget labs and individuals, rendering them virtually inaccessible. This is also why we see so little strength testing related research at a high school or an undergraduate level. Enter the low-cost tensile tester, which only costs $300. That is a 50-fold decrease in price. It can test the strength of plastic, fabric, wires, crimp terminals, and much more. This machine provides an effective solution for material testing in low-budget situations such as startup companies, high schools, and undergraduate labs. To measure the strength of an object, you need to measure at least two variables: stress and strain. Stress is the force per area applied to a material. Strain is the measure of deformation or elongation that occurs in response to stress. To measure stress, the machine uses two fixtures, one moving and one stationary. Each fixture attaches to one end of the specimen. Once the machine starts, the plastic specimen is put under increasing stress. In turn, as per Newton's third law, for every force applied there's an equal and opposite force. The force applied is transferred to the load cell, or force sensor, located right behind the specimen. The load cell measures the amount of force applied through tiny changes in the resistance of a strain gauge placed in the Wheatstone bridge setup. Later down the line, these tiny resistance changes are amplified using the HX711 load cell amplifier. Once processed by the Arduino, this gives our force reading. Now to measure strain. We mount a camera a certain distance above the specimen and track its elongation using moving dots marked by a marker. This is known as an optical extensometer. Using the camera recording and Blender code made by CNC Kitchen, we can extract the elongation values from the specimen. This in turn gives our strain. When you plot stress against strain in a graph, you will get what is known as a stress-strain curve. The curve is separated into the elastic region and the plastic region. From this curve, you will be able to extract the ultimate tensile strength at the graph's maxima in the plastic region, the tensile yield strength at the transition between the plastic and the elastic regions, and the Young's modulus as the slope of the elastic region. This specific stress-strain curve is of an ABS specimen. From this data, we can see that the maximum tensile strength is around 33 to 34 megapascals. Confirming with the technical datasheet for the Polylite ABS which I used, we can see that it is close to the official 33.3 megapascal rating. This $300 machine achieved the same accuracy that a 5-figure machine could achieve. This proves the accuracy of this machine in this specific example. I made this machine in 8th grade, and I'm still improving it today as a high school senior. I've done 2 research projects using 2 variations of this machine, one of which was published, which you are welcome to read about on the Journal of Emerging Investigators. This video is only made as a brief overview of the machine, and I have intentionally skipped certain details. If I got any physics concepts wrong, please feel free to correct them in the comments. Have a nice day.